Hi guys, Ms. O'Connell here. So today we're going to be talking a little bit more about conservation principles and how energy is conserved in different contexts. In order to do that, we're going to first identify what the difference between an open and closed system is, and then continue working on example problems of conservation of energy. So if you took physics last year, you know pretty well and understand what a closed system is. We assume in most of the situations that we looked at that the system is closed. That is not always true. Okay, so when we return from spring break, we'll talk about systems in which could be open and how that affects energy, momentum, etc. in that system. We'll also introduce some work in there the week that we return. Okay, so let's talk about energy. So typical vocab words in physics, right? Energy, force, velocity, acceleration, displacement. Very easy for us to define what a force is, right? What velocity is, what acceleration is. But energy is a little bit more difficult to define. Okay, so energy is as fundamental as the universe, okay? Meaning that space and time are very difficult to define as well. Energy, space, and time are kind of intertwined together because it's fundamental to the principles in the universe. It's very difficult to define energy, but there are a few ways that we can kind of discuss it. Okay, so things that we can say definitively about energy is that energy and work are related. Okay, so we don't know much about work yet, but work is a force applied over a displacement. Okay, we know a lot about force and displacement. So energy allows for the ability to do work. Energy allows forces to occur over displacements. So that's something that we can say about it. That's not the definition of energy, however. We can also say that energy can be stored. Okay, it can be stored in capacitors, which is how your phone charges. It can be stored in springs, which is how the explosions work for the dynamics cards. Okay, we can also say that it translates or transforms. It changes from one form to another. So we can convert light to thermal energy, mechanical to thermal energy, gravitational potential energy to kinetic energy, elastic potential energy to kinetic energy. Okay, so energy, although we don't have one fell swoop definition for it, we know that it's the ability to do work, energy can be stored, and energy can be transferred. The law of conservation of energy states that in a closed system, energy must be conserved. Okay, so let's relate this to a bag of Skittles. Okay, so let's say that the Skittles are our energy, right? So a cool way to kind of think about this, Skittles are our energy, right? We can open up that bag and rearrange the Skittles, right? We can leave them in the bag, we can arrange them based on color, we can make them into a rainbow, or we can have random assortment. The amount of energy and the properties of energy, when we rearrange the energy within the system, still has not changed, right? The sum total is still the same no matter how we arrange it, no matter how it is dispersed among objects in a system. However, right, if we have this form of energy and it's then transferred to different forms of candy, right? So our Skittles, kinetic energy, is transferred to gravitational potential, elastic potential, or thermal energy, right? That energy has changed forms. Okay, when we have one quantity that can be arranged differently and its definition is still the same, or it can be transferred and its relationship or quantity is still the same, okay, that can be confusing. So we must identify or define rather, what kind of system we are identifying or looking at. So we have to define whether the system is open or closed to more easily track these changes in energy. Okay, so we definitely know what a closed system is. Okay, so let's start with that. So prior to this point, we talked about only closed systems. Okay, so we have the universe. Inside the universe is our tiny environment. Inside this tiny environment is a closed system, okay, which we basically isolate the objects that we're studying and pretend that only those objects exist. And we ignore all other outside forces that act on it. So when a system is unaffected by anything in the environment or the universe, okay, we call it a closed system. Okay, we pretend as if it is a universe by itself, right? We look at only the objects, only the space in which we are studying, and we ignore everything else outside of that system. Okay, when it's closed, no objects can leave, no objects can enter, okay, and no outside forces can affect anything in the system. So nothing can enter, nothing can leave, and no forces can affect anything inside of the system if that force comes from outside the closed system that you're identifying. Okay, so we talked about these at length, but open systems are not as familiar to us. Okay, so we still have the universe and the environment, and we still have those objects that we're studying. But in this case, the system, the objects in the system, can be infected by others in the environment and the universe. Okay, so that means that we have to consider the ways in which the objects are affected by the environment while still focusing on only the objects inside the system that we're measuring and calculating information about. So if the system is open, you can kind of see by the little pendulum symbol that objects can leave the system. They might be able to leave the system. And the problems that we look at, that's very rare, that an object will leave the system. But less rare, other objects might enter the system. Okay, so if objects can leave or enter the system and affect the motion, we call it an open system. Okay, if the system is open, outside forces can also affect the motion of the objects in the system. Okay, and we will work on identifying the difference between open and closed systems as we move forward. Let's head to a checkpoint question. So, which of the following characteristics of energy? So which of these are characteristics of energy? You're going to select 2. So pause the video and select 2. Okay, so we should have checked the middle 2 boxes here. See if I can get my laser pointer. There we go. These middle 2 boxes here. Energy can be changed from one form to another, and it has the ability to do work. A and C are false. Okay, those statements are not true. These 2 statements are true based on our definition of energy. Okay, so surprisingly, we can learn a lot about a system by looking at what happens initially and what happens finally, without having to pay attention to the details that occur in the middle. So this is useful for energy or momentum calculations because sometimes the interactions that are occurring during the collision, the interaction, the transformation are very complicated and difficult to analyze. But using conservation principles, conservation of energy, conservation of momentum, even together sometimes, we can determine a lot about a system that we otherwise would not be able to. So that's why conservation is kind of so important. Okay, so let's get back into examples of conservation of energy. Here we're looking at closed systems, okay, because they are virtually frictionless. Once we identify or introduce friction, we will talk about how the system can in some cases be open. For our first example for today, we're going to take a look at a spring gun. This is actually how paintball guns work as well. There's a spring inside. So a spring gun has a spring constant of 250 newtons per meter, and it's compressed 5 centimeters. So as you can see here, when it's loaded up, that spring on the bottom near the trigger, so spring on the bottom near the trigger, is compressed. Let's say it's compressed 5 centimeters. That spring has a spring constant K of 250 newtons per meter. So right now, as the spring is compressing, what kind of energy does the system have initially? Elastic potential energy. Okay, after the spring is released, aka the trigger is released, what kind of energy does the system have? Kinetic energy, right? All of the elastic potential energy in the spring gun is converted to kinetic energy. We need to determine how fast a 0.025 kilogram dart will move when it leaves the gun. So as we said, initially the system has only elastic potential energy. Okay, that's equal to the kinetic energy. Elastic potential energy we know is 1/2 kx squared. Kinetic energy is 1/2 mv squared. On the AP exam, we will most likely not be given numbers. So I'm going to practice as we move, as if this is a section of the open-ended question, solving for the variable and then plugging in after. So technically, we need to isolate v here. So to get v by itself, right, we have 1/2 on both sides. So if we multiply both sides by 2, those 1/2s will cancel. Okay, then divide both sides by m and take the square root. So we find that the expression for v is the square root of the spring constant times the compression of the spring squared divided by the mass. Okay, because this is launched horizontally, all of the velocity will be equal to that expression. Okay, so this will translate, compression in the x will translate directly to velocity in the x. So our last step would be to plug in. Okay, so we'd have to take the square root of 250 newtons per meter times 0.05 meters, don't forget to square it, divided by 0.025 kilograms. In your calculator, make sure you have 0.05 squared times 250 in parentheses, divide by 0.025 kilograms. Okay, and then take the square root. Your calculator does not know order of operations, so it's important to let it know what order to multiply. And we find that the velocity would be 5 meters per second. Okay, example 2. A student uses a spring with a spring constant of 180 newtons per meter to launch a marble vertically into the air. Okay, the mass of the marble is 0.004 kilograms and the spring is compressed 0.03 meters. What is the maximum height the marble will reach? Okay, so this time the compression is vertical. So we vertically stretch a spring downwards. When we release it, a marble is shot up into the air. So similar breakdown here, except the elastic potential energy is converted to gravitational potential energy. So while the marble has velocity when it leaves the spring, the total energy at the end of the transformation will be gravitational potential energy. So we set those two equal to each other. So we know elastic potential is 1/2 kx squared. That's equal to mass times gravity times the height. Okay, we need to solve for h. So we divide both sides by 2mg. Last step, we plug in for spring constant, K, which is 180 newtons per meter, multiplied by the compression of the spring squared, 0.03 meters, don't forget to square it, divided by 2 times 0.004 kilograms times acceleration due to gravity, which we assume is 9.8. When we solve for h, we get 2.066 meters. Okay, so all of the elastic potential energy is converted to potential energy. So this is our initial, this is our final. We ignore the details in the middle, okay, due to the conservation principle. All right, let's try one that's a little bit more difficult. Okay, so let's say that a student uses a spring gun again. Okay, this time the spring gun's spring constant is 120 newtons per meter. The spring gun is used to launch a marble at an angle of 52 degrees to the horizontal. So that means that the spring gun is now launched at an angle. Mass is 0.002 kilograms. Its displacement is 0.041 meters. What's the maximum height that the marble will reach above its initially compressed position? Okay, so we're now combining projectile motion with conservation of energy. So we're going to approach this the same way that we approached the previous problems. We're first going to identify, using conservation of energy, an expression for the velocity. Okay, so just like in our previous example, we use conservation of energy to find an expression for v, and then we plugged in. Okay, so in the previous case, it was completely horizontal, but we can find the y component of the velocity quite easily. So let's start with conservation of energy. So initially, we know that the spring gun has what kind of energy? Elastic potential. Okay. After the bullet leaves the gun, it's going to have kinetic energy. So we plug in for what we know, the definition of elastic potential and kinetic energy. And we're going to solve for v. So we find that v is equal to the square root of k divided by m. Okay, the square root of x squared will just be x. Great. So if all of the elastic potential energy was converted to velocity, this is the expression that we would use. If the gun is launched at an angle or positioned at an angle before the bullet is released, only one component of the velocity will be responsible for the maximum height. So thinking about projectile motion, how can we determine the component of the velocity that we would need? So which component of velocity would we need? Okay, the y component, right? We need the velocity in the y. The y component of the velocity will result in the change in the height. We know that the y component of the velocity is just the velocity times the sine of theta. Okay, so we're finding the y component of the vector by multiplying by the sine of theta. We're going to take v, this expression, and plug in to our relationship from projectile motion. So we have that the y component is equal to the square root of k over m times x times the sine of theta. So we have v times the sine of theta. Okay, so now we can plug in and solve for v. So we're going to plug in for k, m, and theta. Okay, so let's give that a try. So I'm going to take the square root of 120 newtons per meter divided by 0.002 kilograms. Multiply by x, the displacement, 0.041 meters, times the sine of 52 degrees. Okay, so we solve for v, we're going to get 7.9 meters per second. So because this x value here is the displacement of the spring, right? This will be the velocity when the bullet leaves the spring, just like in our first example. So that is the velocity when the bullet leaves the spring in the y direction. Okay, so we have velocity, but we still need to find the maximum height above that initial compression point. So in order to find that height, we have to now think about this kinetic energy in the y, right, is converted to what kind of energy once the object reaches the maximum height in its parabolic path. So that second transformation, right, the kinetic energy will be equal to the gravitational potential energy at its maximum height. Okay, but particularly we're looking at only the y variables. So we plug in, we'll solve for h first, plug in, and we determine that the height of the bullet above its initial compression point would be 3.2 meters. Okay, so it's spring break, ha ha ha, get it? The spring has broke. So next week is spring break. Tomorrow, Friday, I will post optional test review in Google Classroom. It will not be graded. It is not mandatory. Do I think you should do it? Yes. Will I grade it? No. Will I ask you if you did it? No. But I will give you optional test prep with answer keys. And if you want to do well in the AP exam, I suggest that you take a look at it. But it is not mandatory. Have a great break, and I will talk to you on Monday.